Okay, so today we are going to start with the complex analysis. Okay, so let's basically quickly go through the basics. So now you define a complex number z as x plus iota y, and you have this is the real axis, this is the imaginary axis, and over here is z x plus iota y, and another way to represent this is r iota theta, or r cosine theta plus iota sine theta. The Let me just write it here. Theta is this angle, r is the magnitude of this vector, and the complex conjugate is x minus iota y, which would be over here, cosine theta minus iota sine theta, or that would be r, this guy. So what are the relationships between them? Well, so the real part is z plus addition of the complex conjugate divided by 2, which is nothing but r cosine theta. The imaginary part is z minus the complex conjugate divided by 2 iota, or that's r sine theta. What's the magnitude of the vector? That was z square equals to r square x square plus y square, and the angle theta is given by tan inverse y by x, or in other words log of z divided by z star. So you can all check these things. E iota pi by 2 is equals to iota, and on the imaginary axis this is a point on the imaginary axis. Okay, so next we have the power Zn, which is r e iota theta to the power of n, and that goes as theta. This is just algebra, nothing more. Now one can take a few examples. So for examples, let me evaluate iota to the power of iota to the power of iota. So that if I plug in the value of iota, it is e iota pi by 2, e iota pi by 2 to the power of e iota pi by 2. And when I evaluate this goes to e iota pi by 2, and I just put in here e iota pi by 2 times iota, because e iota pi by 2 is nothing but iota, and that gives me e to the power of iota pi by 2, e to the power of minus pi by 2. So sorry, this should be iota over here. So what do we have? I'm just evaluating this exponent times this guy. So xm n becomes xm n. This is what we've done over here. And this I can evaluate as cosine again. This I can write it down as e iota pi by 2 times e minus pi by 2, which is nothing but cosine the angle pi by 2 e minus pi by 2 plus sine pi by 2 e minus pi by 2. Okay. So as another example, let's take another example, example 2. So example 1. Let's say I need to evaluate the summation from 0 to infinity iota pi 2n plus 1 divided by 2n plus 1 factorial. Now you can say it's a power series, so something I'll have to do with the expansion of e pi, which gives me 1 plus iota pi plus iota pi square by 2 factorial iota pi, let me write just another term, by 3 factorial, so on and so forth. And I can write iota minus pi, see, because I just need the odd powers there, so somehow I need to combine such infinite summations in a way that I only retain the odd powers 2n plus 1. So let me try this thing. Iota pi plus get iota pi the whole square by 2 factorial, so on and so forth. So now if I subtract one from the other, I get e iota pi minus e minus iota pi divided by 2, and that yields me iota pi. I'm just subtracting one sequence from the other, plus it's going to yield me iota pi whole cube by 3 factorial plus iota pi whole cube by 3 factorial, so on and so forth. The even terms cancel out and the odd terms will basically be retained. So what do I have? I have nothing but this is exactly what I need over here, right? So I'll have this guy as okay. Now let's see another example, which is z, the complex number, and I have an infinite pattern. This pattern repeats itself. I have the power of half, and I'll have 1, 2, 3, 4. I'll have the same number of closing brackets. So this pattern keeps on repeating itself. It's a recurring pattern, and I need to find what the heck is this pattern. So since it's recurring, so I can put this guy again as z. So my equation becomes and when I square it, it becomes that becomes z equals to half plus minus half 1 plus 4 iota. I just solve the quadratic equation and that gives me the answer. So this is just some drill problems to manipulate complex numbers. Yeah, nothing too profound about it. So next we come to functions of complex variables. A complex function fz typically returns a complex number. That's how I define a function. It's a mapping. You input a complex number and it outputs a complex number. I'll assume z as x plus iota y. So what do I have? In general, I write the complex number when it's input. I'll have another complex number where u and v are some functions. So this is how I define a function of complex variables. Now let's talk about derivative and analyte, whether the function is analytic or not. Analyticity. Okay, so I can take the derivative, I can define a derivative in a regular way, df by dz, and derivative evaluated at a particular point would be the similar way I evaluate the derivative. And from first principles, I know that is defined as the limit z goes to z0, fz minus fz0 divided by z minus z0. That's how I usually denote the limit. So, but if you notice that now it's a two-dimensional problem. I have a real axis, imaginary axis. This is the real z. I have an imaginary z, and I have, the point is that if I am evaluating a derivative at a particular point 0, 0, I don't know which way I approach this limit. Whether I approach this limit from the real part, from the imaginary part, or any other part of angle theta. So I just write it down as, however, there is an ambiguity depending on whether we approach z0 from y equals to y0 or x equals to x0, or as I mentioned, any other line theta equals to theta 0. There is this ambiguity. For example, if I have fz equals to use of xy, my functions, we have xy. Let me try it this way. I have ux plus delta x, comma y minus use of xy plus iota v x plus delta x minus iota v xy divided by x plus delta x minus x plus the iota y minus iota y. So this guy anyways cancels. So this is limit delta x goes to 0. So what does it give me? This gives me something. I'll take the limit. That should give me, if you look at it, I take the limit delta x goes to 0. So that gives me the derivative. This is the derivative I can write down as the partial derivative delta u by delta x. If I just focus on this half, and if I focus on this half, that's going to give me the partial derivative of the function v plus iota delta v by delta x. That's what I get. Now, on the other hand, I can approach the same problem by taking the limit from the other part. This time, taking the limit from the imaginary part of the y-axis. So this was the case when I was approaching this point from the real part, this guy. I can also approach it through the imaginary part, and that's going to be this guy, where I evaluate the limit, and that gives me nothing but, when I evaluate this guy, that would give me 1 over iota delta u by delta y plus delta v by delta y, because I also have this iota here in the denominator. So, well, for the derivative to be consistent, I should equate these two sides. There should be no ambiguity in which way I am taking the derivative. So that gives me the condition delta u by delta x plus iota delta v by delta x is equals to 1 over iota delta u by delta y plus delta v by delta, delta v by delta x. I think I screwed up somewhere. No, I think it's right. Sorry. So when I compare the real and imaginary parts, delta u by delta x minus delta v by delta y equals to 0, and delta v by delta x plus delta u by delta y is equals to 0. So these are the conditions which are called as the Cauchy-Riemann conditions. And since there is no ambiguity when these conditions are met, a function satisfying these conditions is called analytic. So, for example, consider the function fz as ez, or you can also have any other function. Say e x cosine x plus iota sine y. So this is analytical. So how do I say so? What is uxy? This is nothing but ex just a second. Yeah, so let me put this as this guy, cosine y plus iota sine y. So what would that evaluate to? This would be x plus iota y. That's going to be nothing but e to the power of x iota y. That's going to be ex cosine y plus iota sine y. Yeah, so that's my function. This is the function I'm considering. So I have ux as this guy, and the other function of my, remember my function was nothing but, as an aside, fz, I always define it to be u, some u times some v. So I have vxy is equals to ex sine y. So da by u by da by x is equals to ex cosine y, and the partial derivative of da by v by da by y, v with respect to y is exactly the same. And similarly, the partial derivative of u with respect to y, if you evaluate, turns out to be x. So these conditions which we started with over here, these guys are indeed met over here. So this function is analytic. So in general, we saw for one function e to the power of z, but in general it's not very hard to show that fz equals to az is analytic. I can also show that the product of two analytic functions is analytic. Also, a function of the form anzn, where n is a non-negative integer, is also analytic. We can also show that the sum of any two analytic functions is itself analytic. So these are some things, and if you combine all these things, the bottom line is that any polynomial in Z is analytic in the entire complex plane. So that gives you a hint that maybe we ask the question, what about if a function fz can be written explicitly in terms of z it is, what can you say? Well, then it means that it is indeed analytic. So if I can express a function purely in terms of z, then it's an analytic function. And how do I see that? Well, let me calculate the partial derivative with respect to z prime, which is a complex conjugate. And that, by the chain rule, I get plus and if you evaluate this, this gives me the following conditions. This is times 1 over 2 plus but notice, for the partial derivative with respect to z star, the complex conjugate to disappear, these guys have to be 0 simultaneously, but these are nothing but exactly the Cauchy-Riemann conditions, which were the conditions for the analyticity of the function. So whether a function is analytical or the partial derivative with respect to the complex conjugate vanishes, or in other words, the function is purely expressed as a function of fz, only z appears, these are all equivalent conditions. So 0 implies that the function is analytic. Okay, thank you.